Evening everyone. Last class we discussed about heat engines and LMTD method to solve the problems. So today we will solve the problem regarding the counterflow and parallel flow of the heat engine. So here is the first problem. You see here, the consider a very long wire concentric tube heat exchanger having hot and cold water inlet temperature of 85 and 15 degrees Celsius. The flow rate of the hot water is twice that of the cold water. Assuming equivalent hot and cold water specific heats, determine the hot water outlet temperature of the following month. So you have to find the outlet temperature of the heat exchanger, that with the counter flow as well as the parallel flow. The schematic representation is given here. So THI value is given 85 degrees Celsius and TCI value is given 15 degrees Celsius, and the specific heat relation also given, CH is equal to 2 Cc. So now what we have to do, the temperature, inlet temperatures are given. Here we have to assume three conditions. First one is equivalent hot and cold water specific heats and negligible kinetic energy and potential energy changes. We have to neglect it, and no heat loss to the surrounding. So these three assumptions we have to take, and then we have to go for the analyzing part. So for analyzing this, the heat rate of the concentric tube, which means here we can see in the figure that heat exchanger with a very large surface area. So the operating in the counterflow mode, first we will do with the counterflow mode. So to operate in the counterflow mode, we will calculate Q is equal to Q maximum. So it will be C minimum, specific minimum times THI minus TCI. Combining the above relation and rearranging, and we have to find the TH value, its outlet temperature. It will be minus of C minimum divided by CH times THI. This formula we already discussed in last class. So CI plus THI. So that you can write it as minus Cc divided by Ch times Th comma I minus T Pi, then plus THI. And you have to substitute to the numerical values. It's already given in the problem. Then so in this problem, last two classes we have discussing heat exchangers, different problems. Like first three classes, like we explained only in the efficiency part and the output and input power exchange and all. And last class what we did, heat exchanger problem and LMTD discussion also. In LMTD discussion also we did with counterflow and parallel flow. So today also we are finding the outlet temperature of the system heat exchanger in with the counterflow and parallel flow, and schematic representation of heat exchanger is also given. So from here, so here you have to calculate the outlet temperature. So for that, first the assumption what we took is there is no potential energy and kinetic energy losses that we are neglecting, and heat loss also not there to the surrounding. Then now what we have to do, we have to calculate the Q value. It will be Q maximum, that is C minimum times THI minus TCI. Now THO, first outlet temperature we have to calculate. For that, this is the formula we discussed in the last class. It will be C minus of C minimum divided by CH times THI minus TCI plus THI. So then now we have to just substitute the values already given in the problem. Substituting, you will get TH comma 0 is equal to minus 1 over 2 times 85 minus 15 degrees Celsius plus 85 degrees Celsius. So you will get the answer here 50 degrees Celsius. So this will be the outlet temperature in counter.
Where? One second, no, boys, but one second. One minute, that.
Can you please mute it? So this will be the counter flow temperature. Now if you are doing parallel flow operation, hot and cold outlet temperature will be equal. So that is the parallel flow condition. So in parallel condition, TCO will be equal to THO. So hence you can write it as CC equal to CC times TCO minus TCI is equal to CH times the THI, that is inlet temperature, and minus THO. So now we have to setting what outlet temperatures are saying. So we have to give the value like TCO is equal to THO. Then the equation will change like THO is equal to THI inlet temperature plus Cc divided by Ch times THI divided by 1 plus Cc divided by Ch. So this will be the inlet temperature, this HI values, and you have to find the outlet temperature for the parallel flow. And now here also just you have to substitute the values. So it will be 85 plus half times 15 degrees Celsius divided by 1 plus 1 over 2. So it will be 61.7 degrees Celsius. So this is the problems first. First go through the problem and try to solve it, and please give the answer in the chat box, then we will go to the next one. Okay, now we will go to the second problem. It is like it's also for a heat exchanger but with the shape of like cylindrical shape. Now a concentric tube heat exchanger use water which is available at the 15 degrees Celsius to cool ethylene glycol from 100 degrees Celsius to 60 degrees Celsius. The water and glycol flow rate are each 0.5 kilogram per second and determine the maximum possible heat transfer rate and effectiveness of the exchanger. Determine which is the preferred, a parallel flow or a counter flow mode for the operation. And so these are the things you have to find. So it's a heat exchanger is given and you have to find the which method is preferable, like parallel flow or counter flow, and the details which is given is in the temperature it has to reduce from 100 degrees Celsius to 60 degrees Celsius and flow rate also given. Now if you see the schematic representation here, the yeast exchanger pipe is given and in this ethylene glycol in the inlet temperature for both THI is equal to 100 degrees Celsius and outlet temperature for ethylene glycol is given THO is equal to 60 degrees Celsius. Now mass MHI means rate it is given 0.5 kilogram per second. Okay, now what we have
So
to
what is outlet side and inside? What is? Water inlet is inside or outside? Water inlet.
water is outside outside.
External. What is outside? Okay, okay, madam. Right. An area will differ.
Now for solving this, what we have to give, it's a steady state operation and we have to neglect the kinetic energy and potential energy changes and heat loss to the surrounding also we have to neglect. Okay, then we are going to solve the problem here. So it's also similar can be solved in the last class also. Now for ethylene glycol T inlet, it is and its Cp value will be 2650 joule kilogram per Kelvin. Okay. Similarly, water temperature it will be around 30 degrees Celsius and its Cp value will be 4178 joule per kilogram per Kelvin. Now what you have to use C minimum is equal to
Water inlet 30 degrees. Okay. Water inlet 50 degree, madam.
what
Water inlet, which is available at 15 degrees centigrade. Water is 15 degrees, not 30 degrees. The inlet of water.
is here.
Yeah.
Now you have to calculate the C value. So try to calculate first and let me know the answer. Okay. It will be MHCpH.
Two zero eight nine for C of water.
What?
2089, madam, for C. Water side.
Ha. So totally how much you got? 0.5 times 2650, right?
Yeah. No,
And
0.5 times 4178. That is water side.
water. What about the glycol?
Glycol side. Okay. Is 0.5 times 2650.
Huh.
0.5 times 2650. 1325.
Yeah, 1325. Yes. It will be 1325 Kelvin.
Joules per kg per Kelvin. No, joules only. Yeah, it is
Yeah.
kg Kelvin. Okay, okay, right, right.
Now what you have to calculate? You have to calculate the Q maximum times X. That will be C minimum times T HI minus TCI. Okay. So it's already given that all. So now you calculated this Q max value, that C value, it is 1325 for this here, and THI is given 100 minus, and TCI is 15.
15 degree.
Yeah. Now you try to solve this, and what will be the value? How much you got it? The answer will be 1.13 times 10 to the power 5. Will be the Q maximum times X value will be. After that, what you have to calculate? You have to calculate the Q value. It is normal formula, that is mH times Cph times change in difference in temperature. So it will be Thi minus Tci. So that you have to substitute. It will be 0.5 times 2650 times 100 minus 60. So that answer will be the total heat there. So substituting all this, how much you are getting? 0.53 times 10 to the power 5. So this will be the Q value. Now to find that efficiency part, it will be Q divided by Q max. That will be 0.53 times 10 to the power 5 divided by 1.13 times 10 to the power 5. So it will be 0.47. Now what you have to calculate in the parallel flow case, you have to calculate. So TCO will be TCI plus Q divided by MC CPC, that we can write it as 15 degrees Celsius plus 0.53 times 10 to the power 5 divided by 0.5 times 4178. So it will be how much? You have to just calculate that one. It will be 40.4 degrees Celsius. Okay, so now from this we can understand that TC comma TCO less than THO. So parallel flow is possible. So parallel flow mode operation is possible with how we can write it as, that is C minimum divided by C maximum is equal to MHCPH divided by MCCPC. So you will get the value 0.63. This is the cases here. So you have to calculate which one prefer parallel flow, counter flow, and determine the maximum possible heat transfer and effectiveness value. So first maximum heat transfer we found it is 1.13 times 10 to the power 5, and from that Q value also we calculate it will be 0.53. Then efficiency will be subtracting Q divided by Q max. You will get the value 0.47. It's very less effective. And now you have to check it is parallel flow is possible or not. So for finding the TCO value, we calculated TCO value will be TCI plus Q divided by MCCPC. Substitute the values whatever given, and from that what you will get TCO less than THO, which means parallel flow is allowed. Then you have to do a C minimum divided by C maximum. We will get the value 0.63. That is the effective value for the effectiveness value for in the case of parallel. Now we will go to the next problems. It's a theory question which is already you will show in the NPTEL portal assignments for week 6 and week 7. So the first question is, which of the following factor maintain the continuous flow of liquid from condenser to evaporator in heat pipe? So the options also given in that, it's a pressure gradient, temperature gradient, and capillary force and evaporation of vapor. So it will be like um, continuous flow of a liquid from the condenser to evaporator. It will be using the capillary force. Now, which of the following is or associated with the heat pipe? So we have to remember what is heat pipe. So it will be light, cheap and reliable power generating system, or thermal conductivity is very high in the heat pipes and equally effective at very low and low high temperature heat sources. Equally effective at the very high and low heat sources and all of the above. So in this, for a heat pipe is not useful for all the temperature situation. Like it is not useful for high temperature, or it's like it is only for particular for a high temperature heat pipes are different, very low temperature. So option C is not possible. Then the thermal conductivity is very low in the case of the pipe. So this is the answer for this.
Thermal high, madam. Heat pipe, thermal current high, no? Hello?
Yeah, thermal conductivity is high, right?
Yeah, correct, madam. But okay, I want to sound doubt on my two doubts I got in the class section, video section.
Yeah.
Two doubts are, shall I ask the theory part out, madam, please? Hello?
Yeah. Just ask.
But heat, okay, but the liquid in heat pipe, no, sir, please, what type of liquid it is? Any property for liquid is that? Liquid selection, the heat type. In heat pipe, inside, the liquid in heat pipe, what material it is?
Like you are asking what kind of
Material, liquid
liquid will
and
be in
water.
the heat pipe.
Yes, liquid. So I told it is liquid only, but what is liquid? Whether it is water or any fluid or something, I want to ask you. Any property for liquid is there? Any property, specific property for liquid? It should be viscous, it should be low, I like that. Anything?
Like normally it will be in water. Will be water.
Water only it is. Okay.
And some cases also they are using like ammonia and nitrogen also. It depends on the system. How much you have to like what are the condition, like how much you have to reduce the temperature, how much you have to increase the temperature. So accordingly.
Like organic cycle. Like
Yes.
organic cycle that material should be a mixed portion of this ammonia with water. Maybe the
Yes.
two. Yes. Thanks,
So
madam.
such
Thanks.
situation, thermal conductivity will be very important.
Okay. But the ratio of mixing ammonia is important.
Yes.
The ratio of mixing. Okay. You should not lose on thermal conductivity.
Yes. It should not be used by other, and the material also, heat pipe also, it should not lose the temperature to the surrounding. Then
Yes.
it's not
Okay.
effective will be then.
Right. The heat pipe material, it is a liquid. Okay. Heat pipe, very special material for heat pipe. These are a heat pipe. Heat pipe be in the order of normally the size of heat pipe, and if it is bigger in size, no, then maybe a problem will happen in conducting and all. What is the optimum?
Size
Yes.
also should be like fixed. Like if it is higher size, also conduction part will be losing energy.
Yeah. Yes. Okay, what is the optimum of designing a heat pipe? Because the heat pipe is recent development thing. Even though even in my office also there is no heat pipe right now for this. It is this slowly it is developing. But we can utilize all those things. So I told it is maybe wherever the heat we can through the ice, that ice that is using that natural heat from that ground level itself, the ice melting is going on. It is a new concept right now. So that whenever heat available, we can utilize the heat pipe. Then what is the limitation of heat pipe? That point can be dealt with.
Normally, it will be like we are transferring thermal energy from one point to another point, like it's doing vaporization or condensation.
Basic idea is okay, madam. But while designing a heat pipe in the process stream, what's the limitation? Limitation of size, length, this and all characteristics. Even one bearing, for example, pump bearing also can be reduced in temperature. Even the pump bearing has the temperature, inside temperature. Correct, madam? Hello?
Hello, you are asking heat
While
pipe
running,
limitations.
Yes, yes, heat pipe application. We can develop much more on heat pipes. For that, right now, Saar told when the de-icing of the thing, the road in some
Hmm.
Western countries. Like same thing, even in bearing temperature also have some bearing temperature for pump bearing, for pump demand or on demand bearing temperature is there. That can be also used in the heat pipe can be temperature can be reduced through heat pipe. So any other medium, but heat transfer and all.
But one thing is,
We can all
while you are designing heat pipe, the capillary limit you have to,
yeah.
it should be like
Yeah.
more smaller. Then only the capillary limit you can go easily. But
Yes, yes, yes. Well, the bigger in size of pipe will be the capillary force will be less. Right, Anna?
very less. So it cannot like take from one point to another point.
Then what is the
And
practical
similarly,
size for capillary?
hmm,
What is the practical size? Optimum size. Optimum size of capillary. This is for example 1 inch or 2 inch. Cell is how much we can define. This is the optimum size for this heat paper now.
normally it is 100 mm by 100 mm by 100. Like that is the norm. That's kind of heat pipes we are using actually. Like for heat spreader case.
100 mm. 100 mm. Okay, okay, right. 100 mm by 100 mm. Right. Okay, thank you, madam. Thank you, thank you.
And now you say answer this question, which of the following is not true? So
Okay,
size of
size
the
of the
heat
heat
pipe
pipe.
depends on the heat load, and it can recover heat both from higher and low temperature of
Recover.
heat sources, and heat pipe can recover the heat both from the high and low temperature heat sources, and it capable to convert that into the useful work. And evaporator section of the heat pipe, which is filled with working fluid, absorb the available heat to the session. So which one will be the correct answer in this then?
C will be correct.
C.
Yeah, but they ask which of the following are not true.
Not true. Not true means it is D only. The heat pipe
Okay.
can recover heat both high and low temperature heat sources.
Yes. So answer is D only.
It is not true D. It is not true, madam. It is not true means
D
negative
is
answer. Which of the following? Okay.
But about this question, can water heat pipe work below 100 degrees Celsius at atmospheric pressure?
Madam, no.
No, it cannot.
Yes, sir. Please, please explain, madam. Atmospheric pressure only. That is atmospheric pressure 100 is a boil temperature. No.
So water can work below the boiling temperature also, right?
So it should not go vapor. If vapor form, then vapor should go to condensation, then condensate coming to back to evaporator section. Correct, madam.
Hmm.
In heat pipe, water should go to condensate section through vapors, get the heat to the surrounding. The surrounding means to the useful work and getting condensed. But it is being okay. Can water heat pipe work below 100 degrees centigrade at atmospheric pressure?
What? Then what about the freezing point case then? Hmm? What will happen for the freezing case then? Will it work?
Mary will not consider the freezing case because at freezing point it is not water, it is ice.
If
So
it
we
is
are,
below the freezing point, it's not possible.
yeah,
Yeah. Why?
and because below the freezing point it is called ice, right? So it is no longer a water heat pipe.
Then what about the above the atmosphere pressure, like above the 100 degrees Celsius, what will happen?
It will vaporize. Water will vaporize.
Okay, but accordingly the pressure will also reduce, right? So can you anyone say like what is the practical temperature for a heat pipe? Like maximum temperature, upper temperature limit. Let example, if you take a water heat pipe, what will be the maximum temperature we can give then?
100.
So the rule application 150 is the maximum temperature we are setting. Okay, and that envelope, heat pipe envelope will be with copper. Hmm? So it will be if you are giving maximum 150 degrees Celsius water, means saturated water vapor pressure in that copper envelope, it will be like around 477 kilopascal. So it will be okay for that heat pipe. So maximum temperature you can give 150 in the case of water and copper heat pipes. Okay.
Pressure same. Pressure also atmospheric pressure. 150 degree atmospheric pressure, right, madam?
Yes, yes.
150 degree maximum at atmospheric pressure.
No, at that was yes.
Hello?
Hello.
Yes, okay. Thanks. Okay.
What are the material normally we are using for heat pipe?
Copper material.
Yeah, why we are using copper material? What's the important for copper materials? Why we are not using any other things?
Conductivity high. Thermal is high. For copper, thermal conductivity is high.
Conductivity has.
Dot
So
of
how
500.
much temperature it can sustain?
That
From
is
which range to which range? It will be around minus 195 degrees Celsius to 250 degree. That is the suitable range for copper. Okay. So we can use it for low temperature case also, high temperature case also.
minus 199, madam. Minus 199,
minus
correct?
195 to 250 degrees Celsius.
Thanks, thanks.
Okay. Now, if you see in week 7 question, the assignment question, you can see that like thermal efficiency questions also. So now we will do some one or two problem regarding that for steam engine. Okay.
The password is fine.
Already this kind of problem we discussed earlier classes. So can you people do this problem and tell the answer how it will be? A steam engine has a boiler that operates at 500 Kelvin and the energy from the burning fuel changes water to steam and this steam then drives a piston. The cold reservoir temperature is that of the outside air, approximately 300 Kelvin. And what is the maximal thermal efficiency of the steam engine? So how you will find maximum possible efficiency in that case? You have to use Carnot steam engine.
Correct.
Yeah.
Carnot efficiency. That is Carnot efficiency.
But in a real steam engine will work with Carnot cycle.
So, the reversibility is there.
Yeah. In normal real case, steam engine will not work with Carnot cycle, but for finding problems and efficiency case, you are using Carnot cycle steam engine efficiency formula. Okay. So how much you are getting? What is the efficiency? How much percentage?
40%.
Minus.
So it will be 40%. It's very easy to calculate also. Efficiency will be 1 minus Tc divided by Th. So just you have to substitute the value 1 minus Tc divided by 500. So it will be 40%. Now, what about this question? Suppose we wish to increase the theoretical efficiency of the engine. This increase can be achieved by raising Th divided by Th by delta T or by decreasing Tc by same delta T value. Which would be more effective? Same case, okay. So for this case, just try your delta value will be 50 degrees. Okay, like earlier temperatures are 300 and 500. Your delta value you take 50 and analyze this. Then let's say which one will be more feasible. So you have to calculate both cases. What are the cases? First one is temperature 300 and 550, just increasing case. And another case 250 and 500, the decreasing case. Okay, substitute means you can find the efficiency here also and find efficiency here also. Then let's see which one is the more value.
By decreasing Tc by same delta T, it would be
First
more
this
effective.
case, how much is the efficiency you are getting with?
45.45%.
Yeah, it will be 0.45. Yeah, 45.5. And what about this case?
50%.
50%. 0.5. So which one is more?
But reducing upper temperature only. Instead of increasing the inlet temperature Q1, reducing Q2 will be more effective.
Like mathematically this will be right.
Yes.
So what we did, we reduced the this temperature value, Tc value, right? Hmm? That is mathematically we are saying this is feasible, but in practical case, what will happen? Changing
in the temperature.
TH value only possible. Okay.
Yes,
Yeah.
but only in our hand.
Hmm?
Not only in our hand, madam. We can increase the for burning of the fuel rate, then we can increase in the temperature. But how many temperature is depends on the fact.
Yes,
Yes.
yes. Now this one also. This one, if you attend the first class, you can solve this problem. This kind of one problem we solved in I think week 1 or week 2. Just try to solve it. Okay, I shared the link. In that link, you can get all the earlier classes. Okay, I all the lectures actually, whatever we discussed, the problems and all. So see in this problem, what are the things is given? What is the a cyclic heat engine operate between a source temperature is given and steam temperature is given. What is the heat rate of heat rejection per kilowatt net output of the engine? So T1 is given, T2 is given. You have to calculate Q value. Q2 value if W is equal to 1 kilowatt. So what you will do to find it? So T1 is given. How much? 1073 Kelvin. This one, 800 K. And T2 is given. It is 303 Kelvin. Now you have to calculate the Q2 value. The condition is if work will be 1 kilowatt. Okay, so now you know W is equal to Q1 minus Q2. And efficiency part, W by Q1, it will be 1 minus T2 by T1. So that we can calculate here. 1 minus T2 by T1 are how much? 303 divided by 1073. What is the answer for this? How much? 0.
Seventy.
Yeah, 7472. So it is 72. Yes. Now we know the eta value. So from the formula, eta will be what? W by Q1, that is equal to 0.72. Now you have to calculate the Q1 value because W already 1. So Q1 value will be 1 divided by 0.72. So you will get the Q1 value. How much it will be?
1.4.
1.4 you will get. Now you have the Q1 value. You have to find the Q2 value and W is already given. It is 1. So what will be the Q2 value here then? It will be Q1 minus Q2. It will be
0.4.
yeah 0.4. So this 0 point will be the least rate of heat rejection per kilowatt net output for the heat engine. Okay. Now we will go for the last problem for today's session. The question is, a heat engine operate between source and sink temperature to 35 degrees Celsius and 30 degrees Celsius respectively. If the heat engine receives 35 kilowatt from the source, find the efficiency, the net work done by the engine, and heat rejected to the sink by the engine. So you have to find W. W value, Q2 value, and eta value. So eta value you can easily find because T1, T2 is given. So eta efficiency will be 1 minus T2 divided by T1. And from that you can get the W value also. It will be eta times Q1. Q1 is already given. Then you have to calculate the Q2 value. It will be Q1 minus W. So these are the hints. Here you have to find the value for it. How much you are getting the efficiency?
Efficiency 0.403,
Percentage. And what about the work done?
14.12 kilowatts,
In kilowatts. Okay, correct. And Q2 value?
49.12,
Q2 value how much? It is
20.88.
35 minus 14, right? So these kind of questions you can see in your week 3 and week 7 assignments. Okay. So today we will wind up here. So just go through the problems.
So the heat exchanger problem, sir.
Which one?
Hello?
Which problem?
No, heat exchanger problem. The heat exchanger in last assignment number 6. The heat exchanger problem, the effectiveness, R value, P value. This is madam. This is more madam. Finding R value, effectiveness.
Effectiveness, right?
Yes, madam. Last week 7 assignment, week six assignment problem.
You check the last week classes. Okay, you will be there. We solved that.
Okay, thanks.
Yeah.
Right. Okay.
Okay, so I'm stopping here. We will meet the next class. Okay. where we will solve problem related to week 7 and week 8.